The three-body problem. Yes, that's what we're going to do. Okay, so the three-body problem is a classic experiment. It's a classic problem. Let me just say the two-body problem. Let me show you that real quick. One example of the two-body problem is the Earth. There's a continent like that, and there's some continents. And the moon, which is actually about that far away and that big. It's really tiny. And so in this case, the Earth pulls on the moon and makes it move. But since forces come in pairs, the moon pulls on the Earth with the same force. Now, the Earth has a much larger mass, but it does indeed make it also move. So that one's moving that way, that's moving that way, and they both interact with each other. Now, this is the two-body problem because there are two bodies. Get it? Okay. You can actually solve this one exactly. What you do, and I'll make a video on this, you can make this an equivalent one-body problem based on the interaction between two things and some assumptions. Okay, so that you can solve. What if I have three objects, and here I have three moons, and I labeled them A, B, and C because I like it that way. There is no equivalent solution for here. You cannot find the motion of all three objects analytically with an equation, and that's why it's a famous problem, the three-body problem. But you can solve it, and it's not actually even difficult. And I am going to show you how to solve the three-body problem. Okay, so let's make sure that we understand what's going on. So I'm going to assume that there is a gravitational force between these two objects, where I will use this, Fg equals negative g ma mb r hat over r squared. And the negative just means it's an attractive force. So this says that a force between two objects, and we have three here, is going to be the product of their masses. G is a constant. G is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. That's really not important. These are the masses of the two objects. R is the distance between their centers. So I would actually, let's draw this in red. Let's call this vector right there R C to B. So that's the magnitude, and that's a unit vector in this direction. So if I want to find, actually this should be B to C. Well, it doesn't really matter. Let's just, now I've messed up my whole thing. R, C, B, I'm just going to stick with that. And this is R hat. So I need the R hat in order to find the direction back here, and we'll get into all the details of that. But the important thing is that object C has two objects acting on it. Object B pulls on C, and object A pulls on C. So I have two forces. I'd have to calculate both of these gravitational forces. And then same for B, it has two forces. And object A has two forces. And this force right here is the same magnitude, but opposite as that one. So the notation I'm using here is, this is the force by B on C. So BC. And here I could write FBC is equal to negative FCB. So really I only have three unique forces. I have 1, 2, 3, and then the directions change. Now there is one other thing I need here, and that is the momentum of the objects. So let's just say at this instant I have PB, I'm making up these values, PA, and then PC. Okay, so what do I need to do? Number one, calculate F. All the F's. Number two, update the momentum. So let me start, I'll go through all these. And then number three, update position. All. And that's it. So if I do these three things for a short time interval, delta t, then I can just keep redoing it numerically and do a whole bunch of calculations, and I can plot the motion of these three things. And each of these steps is not super terribly bad. Okay, so let's calculate this f. We're gonna do this in Python, but I want to write out the steps better. So here, let's just look at two objects, because if I can do two of these, I can do an infinite number. Okay, so I'm actually going to say this. Oh, I picked a poor origin. Let me put my origin right here. So here is going to be RC. That is the vector location of moon C from the origin. And here is RB. And so I'm going to have these things, right? I'm going to have these positions. And I want to find this vector. And so that's going to be, let's just call that RCB. So RCB is going to be equal to RB minus RC. Right, because this is just like the displacement vector if I went from here to there, but I'm not. I actually have two objects. So I can do that. If I know these two vectors, I can find that. Now I can find the magnitude. I know how to do that. It would just be the square root of RCB x squared plus RCB I'm thinking of multiple things. Y squared plus RCB z squared. Okay, but I can do that in Python. It's not a big deal. I also need to find RCB hat, and that's just going to be RCB divided by the magnitude of RCB. And then once I do that, I can calculate the gravitational force FBC. It's going to be negative G MA MC MB RCB hat, because see, look, I'm finding the force on this one. Oh no, in this case it's actually going to be positive, right? This is where you're going to make a mistake. When I say you, I mean me. Okay, the force on this one is pulling towards that way. So yeah, I did have that backwards. That's fine. And then divided by the magnitude of RCB squared. No, that's not squared. This is squared. Okay. So that's it. That's the force B due to C. Now I just need to do that. I need to find F. I don't need to find CB. It's just FCB I've already found. It's just negative FBC. And then I need to find FBA is negative FAB. And then I need to find FAC is negative FCA. So I need to find all 6 of those forces. And then what I need to do is find FC. This is going to be FAC plus FBC. So I need the forces on just object C. And then the same thing for B. FB is FAB plus FCB. And then I need to find FA, FBA plus FCA. And that's it. So then I've found all the forces. These are the 3 forces on the objects. I don't need to do 6 calculations. I only need to do 3 because some of these I'll have to do twice. Okay, so that's that. And you got to be careful with these signs. You're going to make a mistake. I'm going to make a mistake. Everyone makes a mistake. It's cool. So this is find the force. Okay, next thing we're going to do is update the momentum. So the momentum principle says this. F net is the change in momentum over the change in time. So this is P2 minus P1 over delta T. So if I solve this for P2, I get P2, and where P is mv, I get P1 plus F net delta T. So this says that for any object, A, B, or C, I can do it for all of them, if I know the momentum at the beginning of the time interval, I calculate that force, the net force on it, I multiply it by the time interval, I add it to its initial momentum or its momentum beforehand, and I find its momentum at the end of the time interval. So I need to do this for all of the objects. That is, take their momentum at the beginning of the time interval and find it at the end of the time interval. And this is update momentum. Update P. That's that. That's step 2. Okay. Now, finally, I need to update the position. So I can use the following definition for average velocity. V average is delta r over delta t. So I can do the same thing, r2 minus r1. And these are 1 and 2 in time for a particular object. I can solve for r2, and I get this 3. Update r. r2 equals r1 plus v average delta t. Okay, so now I actually don't have the average velocity. I'm going to actually use the final velocity. I'm actually going to use the final momentum. So I'm actually going to write this. I just said actually now 4 times. Okay, that was weird. So r1 plus p2 delta t over m in general. So for instance, if I want to do this for object B, this would be, well, that's a vector. RB2 equals RB1 plus PB2 over MB delta T. So I do that for A, B, and C. Okay, so we're doing pretty good here. I can start programming this because, but there are some things I'm going to need to figure out. One, I'm going to pick the masses. I'm going to say MA is the moon in kilograms. And I don't remember what that is off the top of my head. I'm going to say MB equals 1.5 moon, our moon, and then MC equals 2 moon. Now I need their starting positions. So let's say, I'll put one of them at the origin. So let's say RC equals 0. It's at the origin. RB is going to be equal to, let's call this REM is the distance from the Earth to the moon. So this is going to be equal to, I'm just looking at that picture in my mind and thinking about this. Right, so that's at the origin. So RB is going to be the vector. I'm just going to put REM 0.8 REM 0. And then RC is going to be equal to, again, I'm just picking stuff here. Let's say 1.5 REM 0, 0. Finally, I need momentums. Oh, I need 2 more things. So P, I don't really know these momentums. I'm just going to guess. Okay, I'm not even going to write down something. I'm just going to guess in the program. But there is one other thing I do need to know, delta T. I can't use delta T of 0.01 because that would be, think about the Earth orbiting, the moon orbiting the Earth. It takes, what, 28 days. Okay, so if I do something like probably an hour, delta T equals 3,600 seconds. That might work. But I'm going to play with that. So I'm going to play with the P initial. I'm going to play with the time interval. I'll use those things. And we're going to program this in Python. And we're going to do the whole thing. And I'll see you guys over there on Python. This way. My computer's over that way. Come on. Come on, let's go. Okay, I see you made it over to my computer. It's not too difficult. I'm just a few feet away. Let's get started with the code. So just a quick note, I'm using Python. This is actually GlowScript vPython, so it includes some visual objects. I'm doing this in an online code, trinket.io. It's pretty awesome. I'll link to the code below. Down there, I'm pointing and you can't even see it. I don't know why I'm even pointing. I'm still pointing. Okay, so I've already entered some information to get a little head start. The first thing is this gravitational constant G. This is the mass of the Earth's moon, and this is the distance from the Earth to the moon. I use that in my initial conditions. Okay, so the first thing I'm going to do, let me just show you this really quickly. If I do sphere and I run it, in case you haven't seen GlowScript vPython before, it has this visual module in there that makes these three-dimensional objects. So look at that. I can rotate that around, I can zoom, and all I'll do is make this built-in object sphere. So I'm going to make my moons, my 3 moons, as spheres. Let's just get started, and I'll fill you in with the details as we go on. So first I'm going to say MA. Should I call it that? Yeah, MA is moon A, and it's going to be a sphere. I need to give it the location of that sphere, and I already said that it was at, oh, where'd my diagram go? I said it at the origin. So it's going to be at equals vector 0, 0, 0. The other really great, super awesome, wonderful thing about Trinket is built-in vector variables. So I can use vector operations and things like that. Now I also need to give it some other parameters. I could possibly give it some other parameters. One thing is the radius. So how big is this moon going to be? Let's just try something like this. Let's try, let's say radius equals REM, which is the distance scale that I'm going to be using, divided by 20. I'm just making that up, and I need to give it a color too. Color equals color dot red for now. Let's run this and see what it looks like. Okay, so it looks the same except that it's red because Python zooms in automatically, so it wants to fill up stuff. So let's see what it looks like after I add the other mass. So MB, as I said before, it's also a sphere. Its position I gave as the following. I wrote this down. Vector REM, 0.8 REM, 0. And let's give it the same radius just for fun. Well, let's do it a little bit different. REM, let's see, it actually is more massive. So I'm going to say REM divided by 18, and let's make it yellow. Okay, now we should see something. Okay, that's good. I think I'm pretty happy with my choices. These are not realistically scaled sizes because if I did make them the right size, they're really, really tiny and it's hard to see. So we're really just plotting the motion here. So I'm happy with that. Let me add one other thing here. Make underscore trail, not trial, trail equals true. Put that down here too. So what this does is that when the object moves around, it's not moving right now, you'll leave a trail, and that's kind of cool. Okay, last moon MC equals sphere, position equals vector. I said it was at 1.5 times REM, 0, 0, and it has the biggest mass, so let's say it has a radius of REM divided by 15, and let's say it's cyan. Color equals color dot cyan, make trail equals true. Run it. You always want to run these things after each little iteration to make things are working. Okay, so it looks good. And yes, you can rotate this around, like I said. See, I'm rotating around. I can zoom in. Yay. Okay, now I need some other things in here. I need the masses. So here I'm going to say MA dot M equals. So the mass, I'm using this object orientation notation so that I can say, I can add this parameter .m to the object MA, and I don't have to worry about another whole variable. It just makes it a little bit easier. So I said that was the mass of the moon, so it's going to be moon mass that I have up top. MB.m equals 1.5 times moon mass. MC.m equals 2 times moon mass. Okay, we're moving along. Now, the other thing I need is my initial momentum. And I didn't put a value here in the previous work, and I decided to not. Well, I am. I'm going to say MA equals, let's just write it like this. It's going to be MA.P for momentum equals MA.M times vector 0, 0, 0. And that way I can just change the velocity and I already have the mass and do the same. Let's start them all from rest. MB.P equals MB.M times vector 0, 0, 0. MC.P equals MC.M times vector 0, 0, 0. Okay. I need time. I need the time step, which I said was an hour, 3600. So it's important to realize that our units for momentum and for the forces, they're all in the region of seconds. So I can't put one and just say I'm going to use hours as my unit because my other quantities are in units, technically in units of second. G right here, this is seconds, okay? When I calculate the force, it's going to be seconds. So I have to do this in seconds. And this may be too big or too small. I don't even know. We're just going to have to wait and find out. Okay, now I'm going to make a loop. So let's just say, let's run this for a month. So I'm going to say while t is less than a month. I shouldn't have done that. Let's see. T max equals, a month is going to be 24 hours, 24 times dt times 28. Is that right? Yeah, okay. So while t is less than t max. The next thing I need is to, oops, I don't want to go down that far. Scroll down. Okay. The next thing I need to do is this statement. Rate 100. So this tells the visual part over here to not do more than 100 calculations per second. And this may be too fast or too slow. I don't know. I'm just going to put it there and I can change it. Now, the next thing I need to do is to calculate my forces. So I'm going to first calculate the position vectors. So I'm going to say R, A, B. This is the vector from A to B. So it's going to be equal to MA dot P, no, 2B. So it's going to be MB dot POS minus MA dot POS. Now I need to do the A to C. RAC equals MC dot POS. So when I say MB dot POS, that means the object MB and its POS attribute. And up here, that's this vector up here. Okay. So MC.POS minus MA.POS. And finally, I need to do RBC equals MC.POS minus MB.POS. So I have the vectors. Now I need to calculate the forces. So I'm going to say FAB. This is the force that A exerts on B. And the vector I have is from A to B, right? So if this is A and that's B, the vector is like that, okay? So the force on B up here is going to be in the opposite direction. So I'm going to say is equal to negative G times MA dot M times MB dot M times, now I need to multiply it by the unit vector R, which is just going to be norm RAB. So remember that so there's a built-in function in Python to find the unit vectors, and it's called norm. So I don't have to do that all by hand. And I'm going to divide that all by the magnitude of RAB, again, built into Python, closed script Python, mag RAB and squared. Remember, in Python, squared or raised to the power is star, not hat. Okay. So now I can calculate our FAC equals, it's just going to be the same thing. Should I just copy that? Let's just see if that works. FAC, Control C, copy. And I'm going to change this from AC, AC. I'm trying to keep my notation consistent. So this is the force on C, right? And then I need one more, and it's going to be FBC equals that whole thing. So it's going to be BC BC BC. Okay, I think that's good. So now I have 3 of the 6 forces. I can find the other ones just by using these. Now, the next, and I have to do this every time because these moons are moving. I need to redo it every time. So the next thing I'm going to do is update the momentum of each object. So I'm going to say MA.P equals MA.P plus the net force on A. So this is going to be right here. None of these forces are on A. This is A pulling on B, and this is A pulling on C. So it's actually going to be the opposite of those two. So it's going to be negative FAB minus FAC, right? Because those are the equal and opposite forces. And multiply that by dt. Now I'm going to do the same thing for B. MB.P equals MB.P plus. Okay, so what forces are acting on B? I have FAB, and then I have FBC acts on C, so I actually need a negative right there. So it's going to be minus FBC times dt. And then finally, MC.P equals MC c dot p plus I have FAC plus FBC. Just a quick reminder down here, this is a set equal to sign right there. So that's why these mass ma dot momentum doesn't cancel over here, because it's not. It says take that old momentum, add this stuff to it, and make that the new momentum. So it's not that. So I've done now that I've done calculate the position, I've calculated the force, I've updated the momentum. Now I need to update the position. So let's say ma dot pos equals ma dot pos plus the momentum ma dot p times dt divided by the mass ma dot m. Do that for b. mb dot pos equals mb dot pos plus mb dot p times dt divided by mb dot m. mc dot pos equals mc dot pos plus mc dot p times dt divided by mc dot m. I have to have made a mistake somewhere, right? T equals t plus dt. I think I need to update time. I think that's it. Let's just go up here and save. Save it. And run it. What do you think? What do you think? Is it going to run or is it going to crash? I'm giving it a 84.5% chance of working. Is it working? Okay, I think it's going to work. I think it's just going really slow. So let's increase this to 1,000. Does it give me an error? Oh, it did. That's why moon mass is not defined. Moon mass. Oh, because I mistyped up here. Moon mass. It's moon mass. Check that out. It worked. Okay, let's change this back down to 100. And yes, things get a little crazy, but it works. So they're moving. They're all moving towards looks like. Now, over there, what happened was the two masses got super close together, and they kind of eject each other. The gravitational force increases super fast, and that's what causes these things to like shoot out, because it gets a giant force on there. So let's go up here and give it an initial velocity. So ma is this particle down here. I want it to go, let's say it's going in the x direction. And I need to pick a velocity. I'm just going to pick something. I'm going to say it's moving in at, let's say, 4,000 meters per second. MB is, where is that one at? That one's up at the corner. Let's make that move up and to the left. I want them all to kind of be orbiting. So let's say negative 2,000. Oops, I missed my thing. And up at 1,000. And then C was the one up there. I want it to move, let's say down, let's say negative 1,000 and negative 1,000. Okay, let's just see what happens. Okay, maybe too fast. That one's going in the X direction. I actually want that one to go down some. So let's pick this at 1,000, negative 500. I think my velocities are all too big. Oh, that's 5,000, negative 500. That one's going too fast. They're all too fast. Okay, so let's slow everything down by a factor of 10. Let's just see what happens then. Okay, I think I'm pretty happy. One thing you're gonna notice right here is that the center mass is not constant, because I didn't have the total momentum equal to 0. So I could do something like this. Let's do this. Let's say mc dot p equals negative ma dot p plus mb dot p. So this is going to make the total momentum 0. because I'm saying that the particle C is just moving, has the opposite momentum of those other two. Let's just see what happens. Okay, I still don't like that red mass is going too fast. Let's move this down to 100. It gets so fast it gets far away, and it doesn't really interact much with the other balls. And then that one, the cyan one, I think, well, okay, I think I'm done. Okay, I'm done. I think this is good enough. Let's just run this for a little bit longer, for 4 months. Oops, not dollar months, 4 months. Why am I doing it 4 times? Just so we can see what happens. It's going really slow. Okay, but I think that I have solved the 3-body problem. And you can use this code, because there's a lot of things that I have not answered yet. Oh, there's going to be an explosion right there. Oh, look, they missed. Oh, that's cool. Okay. Is momentum conserved? You can check that, right? You can make a graph and plot, is momentum conserved? Is energy conserved? That should be conserved too. Plot that and find out. Can you make a stable orbit? Could you make these things in more stable format, like get them all moving in the same circular path? That you can do too, and it's pretty cool. Actually, I'm kind of excited about these two things. Change the masses. Make this the sun, earth, and moon. Make them orbit each other. That'd be cool. Now, the scale gets really crazy there, but you can do it. Okay, so I think I've taken enough of your time, but I have shown how to do the 3-body problem. The code will be below. You guys have fun.